In this video, I'll review how to interpret regression tables. Among other things, I'll talk about logged dependent variables, continuous and dummy independent variables, quadratic terms, and interactions of independent variables. Nothing I say should be particularly new, but it's always nice to get a refresher before you dive into a stack of research articles that are full of regression tables. This table is typical of what you might see in a research article. Each column reports the results of a single regression. So in this table, we have 4 regressions. The columns are often labeled with the dependent variable, and here the dependent variable is log monthly income for each regression. That's what ln wage signifies, log monthly income. The first regression is simple and bivariate. It simply includes years of education as an independent variable. The second regression adds variables for experience and experience squared. The third regression adds a dummy variable for male. And the fourth regression adds an interaction between the male dummy variable and years of education. Most regressions that you see reported also include an estimate for the constants, as well as the number of observations in each regression. In this case, each one of the regressions reported is estimated using 8,170 observations. All of these regressions were estimated using data from the first wave of the Mexican Family Life Survey. It's a population survey of households in Mexico conducted in 2002. Each observation corresponds to an adult who reported at least some labor income in the last month. And as I said, income is measured in thousands of pesos. Let's look more closely at the first column. As I said, this bivariate regression contains exactly one independent variable. That's years of education. First step when interpreting a regression is to immediately recognize what the regression model is that's being estimated. In this case, it's log wage. It's a linear function, beta 0 plus beta 1 years of schooling plus an error term. If we take the expected value of both sides, conditioning on the independent variables, so expected value of log wage, conditional, I'm going to write x, and that's going to represent all the independent variables in the regression. In this case, that's just education. Okay, if I take that expected value, the expected value of a constant, well, it's not, there's nothing random there, so it's just beta 0. Beta 1 ed, since I'm holding all the independent variables constant, this is just another constant. We have beta 1 ed plus, well, what's one of the main assumptions, one of the critical assumptions of a linear regression model? It's that the expected value of the error term, conditioning on any of the x's, is 0. That is, it's a little bit weaker assumption than independence, but you can think about epsilon and the independent variables, or the x's, as being independent. If they're independent, then this conditional expectation will be equal to 0. And so that's exactly what we're taking right here. So this is just 0. So it just goes away. Okay, now we can take the partial derivative of both sides. And if we do that, we take partial derivative of expected value, log wage given x, with respect to education. Okay. Well, the partial derivative of a constant with respect to a variable is just 0. Beta 0 is not changing with an increase in education. Beta 1 plus ed, well, that's just beta 1. Okay. So this is just beta 1. So what's beta 1? Well, it's how do we expect wage, the log of the wage, to change when we increase education by 1 unit. Now in this regression, beta 1 hat, our expected value, is simply 0.0985. So as education increases by 1 year, log wage we expect to increase by 0.0985. Now, because the coefficient is pretty small, pretty close to 0, we can interpret this as the multiplicative change in the expected wage itself. That is, we expect an additional year of education to increase wages by about 9.85% increase in wage itself, not logged wage. Now the stars that we observe in most regression tables correspond to how significant is the test, how significantly different is this coefficient estimate from 0. That is, we're looking at this test that beta 1 equals 0. The true beta 1 is 0. Okay? Those stars represent the p-value of the test. There's almost always a legend at the bottom of the table that tells you what the stars signify. 3 stars is pretty significant. In this case, 3 stars means the p-value is less than 0.001. Okay, if that's less than 0.05, we usually call it a significant result. Okay. Now in parentheses below the p-value, or below the point estimates, okay, there's always almost always a number. In this case, the legends tells us that it's the t-statistic for that test. Now remember that when a t-statistic is greater than 2, that means that the test, we can reject the test with a significance level of 5%. Okay, 41 is a lot bigger than 2, which is why we have such a why we have the 3 stars. It's a very, very significant result. Which is not surprising because we do expect wages to be higher for individuals that have more education. Now, when you're looking at regression results, it's important not to just skip right to the stars. Don't just look for significance. Sometimes you'll see very small point estimates that have very small standard errors. And even though the coefficient might be insignificant, we still learn something. In that case, we learn that the true coefficient is likely to be very small. We could build a confidence interval if we wanted to. Now, when we have an insignificant result with a very large standard error, well, we can't learn very much from our data in that case. Now, let's take a look at this constant. The constant represents the expected value of log wage, given our independent variables, when all of those independent variables, in this case just education, equals 0. Okay, that's going to be beta 0. So in this case, 0.0572 is what we expect log wage to be for someone with 0 years of education or no schooling at all. Okay, and if we exponentiate that, if we take the exponential of beta 1 or beta 0 hat, okay, that's exponential of 0.0572, okay, that gives us 1.059. Okay, and that means someone with no schooling, we can expect to have a monthly income of about 1,059 pesos per month. Now let's take a look at the second column. This is the model where we've added experience and experience squared. And so our model is log wage, beta 0 plus beta 1 education plus beta 2 experience plus beta 3 experience squared plus epsilon. We can also rewrite this as just the expected value of log wage given all of our x's, okay, is just this. Our estimate for beta 1 is 0.114. Our estimate for beta 2 is 0.0364. Our estimate for beta 3 is this minus 0.000488. Now, suppose we want to know what the effective experience is. we don't just have experience, we also have this quadratic term. And so when we take the partial derivative of this conditional expected value with respect to experience, we get beta 2 plus we get the term that comes from over here. We get 2 beta 3 times experience. Okay? If we plug in our coefficients, this is going to be, our estimate is going to be 0.0364 plus 2 times minus 0.000488 times experience. Okay? Because the coefficient on the quadratic term is negative, that means the marginal effective experience decreases as adults gain more experience. The first year of experience, that is this expression plugging in 0 for experience, increases wages by about 3.5%. That comes from this piece right here. But after 25 years, that is if we plug in a 25 right here, this whole thing gives us 0.012, which corresponds to about a 1.2% increase in wages for each year of experience. Now, note that when we control for experience, our estimate of the returns to schooling increases. Okay, it went from 0.0985 to 0.114. And that's because we're not just comparing wages of people with different years of schooling like we were in the first regression. Now what we're doing is we're implicitly comparing wages of people with different schooling, but we're holding their experience constant. We're comparing people with the same experience, but different levels of schooling and seeing how their wages differ. Now in general, older people have less schooling. Over time, people are getting more and more schooling, and so the older people are stuck with less schooling. Those older people also have more experience, and so if experience has a positive effect on earnings, and it seems to, then it's going to be a confounder in the first model. That is, by omitting, when we omit experience from the first model, we're getting a biased estimate of the causal effect of education. So in that first model, what's happening is the coefficient on education is capturing both the causal effect of schooling and the fact that these adults that have more, that those adults with more schooling also have less experience, and that lower experience is driving down their wages. And so this is going to be biased, and it's going to be biased low relative to this estimate right here. All right, let's go on to the third column. Now in the third column, the model adds a dummy variable that's equal to 1 for males and 0 for females. So we have log wage. In fact, we'll go straight to the conditional expected value. We have the expected value of log wage given all of our independent variables, beta 0 plus beta 1 education plus beta 2 experience plus beta 3 experience squared, and now we have a new term, beta 4 times male, which is either 0 or 1. Okay. In order to figure out what beta 4 means, we can't just differentiate with respect to male, because male is a dummy variable. It's not a continuous variable. All it takes is a 0 or a 1. But what we can do is we can evaluate this expected value at male equals 1 and male equals 0. And so if we take expected value of log wage, holding all the x's constant and holding male equal to 1, okay, what we get is beta 0 plus beta 1 ed, beta 2 experience plus beta 3 experience squared plus beta 4, plugging in a 1. Okay, if we do the same thing, conditioning male equal to 0, okay, all of this is still there, but that part's not there. And so if we take the difference between these two terms, we get beta 4. So what's beta 4? Beta 4 is the difference, holding everything else constant, between what we expect for males and what we expect for females. And that difference in this table, beta 4 hat, our estimate, is 0.461. Okay. Now, this is too large for that approximation that we used before to work. So saying that this means that males get paid 46% more is not that great an approximation for what's really going on. So what we actually need to do is we need to exponentiate beta 4 hat, and to get a number, and that number we get when we do that is 1.59, and that's actually the multiplicative effects that we expect to see for males. That is, the expected premium in wages for men with the same education and the same experience over women is actually about 59%. So now let's take a look at that fourth column. In this model, we're adding yet another term, which is this interaction between male and education. So what we have is we have the expected value of log wage holding all of our x's constants. Now it's going to be beta 0 plus beta 1 education, beta 2 experience, plus beta 3 experience squared, plus beta 4 male, plus beta 5 male times years of education. Okay. Now let's see what we get when we take the partial derivative with respect to education. Because what happens is it's not as simple as it was before. Before, when we did this, we took the partial of this thing with respect to education. We just got beta 1. But now education appears over here in the interaction. And so what we get is beta 1 plus beta 5 times our dummy variable for male. Okay? So plugging in male at 0, so for females, our returns to education is just going to be beta 1. Well, that's beta 1 hats, okay, which in this fourth model is 0.138. Okay, so the returns to education in this model for females are estimated to be 0.138. Now for males, it's going to be beta 1 plus beta 5. That is plugging in the 1 for male. Well, beta 5 in this case is the coefficient on the interaction, and that's minus 0.0361. And so what we get when we add those two together is 0.1019, which is about 10.2%. Okay. Now beta 5, you'll know, of course, is the difference between the two, and it's negative and it's highly significant. So what we can say is that the difference between the returns to education for men and women is highly significant, and the returns to education for men are about 3.6% percentage points lower for men than they are for women. Now note also that when there's an interaction in the model, we have to be very careful interpreting the main effects of the two variables. So take, for example, the coefficient on male. Now, when we take this expected value and we hold male constant, what we get is this whole term, all of it, beta 0 plus beta 1 ed, beta 2 experience, beta 5 experience squared, beta 4 male, plus this end piece. And so for female, those last two pieces go away. And so what we end up with is now when we have the interaction in the model, is the raw effect, the raw difference between males and females, so we're going to call it just the effect of being male, is actually beta 4 male, rather just beta 4, sorry, beta 4 plus beta 5 times education. Okay. Beta 4, our estimates, is 0.74. Okay, that's beta 4 hat, 0.74. Okay, and beta 5 is 0.138. Okay. Actually, no, beta 5 is not 0.138. Beta 5 is minus 0.0361. So what we're saying here is the effective male for the average difference we expect to see between males and females is about 0.74 in the log wage for individuals that have no education, but that gap drops as education increases, which of course is perfectly consistent with what we just looked at before. That is, the higher returns to education for women. So we expect to see, as men and women both acquire more education, that the gap in their wages drops in this data. All right, so let me stop there. We've looked at logged dependent variables. We've looked at dummy independent variables, continuous independent variables, quadratic terms, and interactions. So you should now be ready to tackle and interpret basic regression tables on your own.